Afternoon, everyone, and thank you, Ivan and Carlos, for the invitation to come here. I think it's a very nice format, and please feel free to ask questions at any time in between. I will use the strongly interacting fermions that Ivan introduced just before lunch, and I will discuss their quite remarkable transport properties. So I will start by giving you just an overview of what is the state of the art of the phenomena, then how we can treat them theoretically, and along the way we will encounter several open questions, and then towards the end I will give an outlook. So, well, in the last almost 20 years there have been various studies of transport for strongly interacting fermions in ultra-cold atoms, often near resonant interactions, because that is often the interesting case. And one key experiment was when you have, say, a cloud of up atoms and a cloud of down atoms, and then you let them collide. So because the interaction, the zero-range interaction, is just between opposite spins, each of these clouds are non-interacting, but when they now collide and touch, they are very strongly interacting. Now, what happens? Imagine these clouds are many orders of magnitude thinner than air, and they have a zero-range interaction. In fact, they don't just pass through each other, but they bounce off. So you have bounces, and then after around a millisecond or so, after several bounces, these clouds will merge. And at this point, one can read off a spin diffusion coefficient that characterizes the hydrodynamic motion of mixing these two clouds. So this kind of observing shock waves in such a dilute gas is very remarkable. Then also, now already many years ago, is that this fluid, the resonant interacting Fermi gas, has a very low viscosity. It flows almost without friction. So the question is, you have some obstacle, and you have the fluid flowing around it, and the question is, how large is the friction for that? So the friction would usually be characterized by the shear viscosity eta, which is a dimensional quantity. So in order to get something comparable between different systems, one can normalize it by the entropy density S. And for these systems, this was found to go, well, down to roughly 1.5 h bar over k Boltzmann. So in this combination, all material properties cancel out, and it's just fundamental constants that remain. There have been conjectures from holographic duality that claim a lower bound. This unitary Fermi gas is in fact the non-relativistic system where the lowest viscosity has been observed, closest to this conjectured bound from string theory. So this is nearly perfect fluid. Now this is one particular transport property, but oops. No, sorry. Such questions of bounds to transport have been considered for many different transport properties, and one can draw a comprehensive picture of many of these if one plots, say, a diffusion coefficient versus temperature. And generally, if you here somewhere we have a Fermi temperature, here somewhere we have the critical temperature toward the superfluid. So here's superfluid, here's normal. Then in many cases, this diffusion coefficient is coming down and then, and then saturating for the degenerate Fermi gas towards something that goes like h bar over m. This has the right units of area squared over time, area over time. So this was then recognized as a quantum limit to diffusion. And now the precise number here can be 1 or 2, it doesn't matter, but the fact that it goes here toward, doesn't go below this limit is a quite generic feature. This has been seen for shear viscosity, for spin transport, for various other transport properties, also sound attenuation for first and second sound. Now, when you go to TC, say in sound attenuation, there will be some critical fluctuations that lead to a divergence here. And then below TC, it's still roughly in that ballpark. So here we have the feature of quantum limited diffusion. And how this arises can be understood in a very hand-waving way from kinetic theory. So in kinetic theory, the diffusion is determined by a typical velocity of particles times their mean free path. Now, if you have a Fermi gas, then you would estimate you would take the Fermi velocity, h bar kf divided by m. And if the mean free path in a gas cannot become shorter than the particle spacing itself, then this would provide a lower bound where, so for the mean free path, we say it cannot become smaller than 1 over kf. And you see kf cancels out, and we are left with something like h bar over m. That is a very hand-waving argument. Reality is more complicated, but serious calculations of this quantity require a lot more work, in particular in this strongly interacting region at unitarity and near TC. So a third observation is that the transport time or transport scattering rate tau inverse for many of these properties scales linearly with time. Roughly in a temperature window between Tc and Tf, and for most, then for higher temperatures, eventually scattering at very high energies will become inefficient, and then the scattering rate goes down again. And this, again, is observed for several of these transport channels. Yes, please.
So here we are talking about systems in the continuum, right?
That's in the continuum without a lattice, that's right.
In the lattice, at high temperature, we expect the diffusion constant to actually sample.
Right. No, that's different here. Mm-hmm. Right. And well, that the diffusion constant goes up here is, well, it has been found already by Maxwell that, say, shear viscosity at very high temperatures does not depend on density. And if you now fix density and ask for the temperature dependence, it goes up by a power law of 3/2. That's just a consequence of this density independence expressed in these units. Now, how can we describe this theoretically and how can we make progress? So one approach is, of course, hydrodynamics. In hydrodynamics, it's an effective model. So you need some input externally. That is the equation of state and the values of the various transport coefficients like shear viscosity, thermal conductivity, and so on. And once you have these, it works very well. But the question is, how can we actually compute these transport coefficients? And another question is, well, if such a quantum limited diffusion is found for various transport channels quite generally, and also this very low friction is something that is found not only in cold atoms, it has been measured in helium, it's just slightly higher. It is measured in, say, a quark-gluon plasma in high energy. So it's observed in various very different areas of physics. And the numbers here are comparable, right? Give or take some factor, but it's in the same ballpark. And so the question is, of course, the microscopic interactions in these systems are very different. But maybe at strong interaction, these details don't matter anymore, and maybe we can find a common description that captures some universal essence of these different systems, or at least part of it beyond the specific details. So, a first attempt to compute, say, transport coefficients is by Boltzmann kinetic theory. So here one works with the distribution function of particles in phase space. So one has a function f of r, p, t. And then how this evolves is described by the Boltzmann equation. So you have how this f changes with t, and then v dot the gradient of the distribution minus the gradient of the potential times the p derivative of this f. So this is what you would get as the Liouvillean evolution. And this distribution function changes not only by the flow in phase space, but also by collisions. And this goes on the right-hand side. So here we have the so-called collision integral. While mean field effects of the interaction would usually lead to a modified dispersion relation that goes on the left-hand side. So this collision integral can usually be expressed as by some big integral that involves the scattering cross-section. Consider we have a scattering of two particles, 1 and 2, that go to new states 1' and 2'. So we need the scattering cross-section. We need the relative velocity of incoming particles. And then we need the thermal occupation factors. And there is basically the case when you're starting in state 1 and you scatter it into a different state. That is the loss term. And so it says if we have the occupation, if the occupation probability for the first particle times for the second particle, and then for fermions, we also ask that the output states 1' and 2' are not occupied. That implements the Pauli principle. Then this scattering process goes out of our original state, so it reduces the probability to be in F. But then, of course, the whole process may be reversed. So we also get a gain term with negative sign and inverted occupation factors that involve 1 minus F1, 1 minus F2, F1 prime, F2 prime. Now if these are distributions in equilibrium, there are no net collisions, but if you go a little bit out of equilibrium, there are collisions that drive it back to equilibrium, and then this collision integral gives you a typical time scale on which this happens, and that is what then determines the transport scattering rate. Now, at high temperature, this becomes exact, and it works very well. So basically, using what we learned in the previous talk, the scattering cross-section is given by the, now this is a different f, it's the scattering amplitude for a certain relative momentum k, modulo squared, and then in vacuum for the cold atoms, this has a very simple form. It's 1 over the relative momentum squared plus 1 over a squared, the inverse scattering length squared. And if you now go to unitarity, that is the scattering resonance, the second term vanishes, and you have a very simple scattering cross-section. And in this case, you can even solve these collision integrals analytically, and it's so simple that it would actually serve as a nice textbook example for scattering theory, perhaps even simpler than the Maxwell potential r to the minus 5 or what people traditionally use. So this is a case that works very well. Now, if we go to lower temperature, still above Tc, so we are aiming for the degenerate phase, then these 1 minus f terms, the Pauli blocking, is important. And it has two effects. So if you look back at this collision integral, it has these 1 minus f terms, right? So it says you can only go scatter into this new target state if it was not yet occupied. Now, at lower temperature, this reduces the phase space for scattering, and so it tends to lower the scattering rate. So let's draw a picture of this. So we have the scattering rate versus temperature. At high temperature, say this comes up, and then when we reach the Fermi temperature, roughly, you would think that it would saturate. So this would be the effect of Pauli blocking. This is, say, for weak interaction. Now, if we go to unitarity, then overall the scattering is stronger. So we have something higher here. But then Pauli blocking would again tell us that this should now curve down. Actually, this eventually goes down. But there is, so one is the effect of the reduced phase space in the collision integral. But there is now a competing effect that has the opposite sign. And that is that in this scattering cross-section, this is given by repeated scattering between two particles. But also for this, not only for the final target states, but also for these intermediate states, we have the Pauli blocking. And there it has the opposite effect. So here, it actually increases the scattering cross-section. So if we do the Pauli blocking also here for the internal fermion states, and if one includes this increase of the scattering cross-section, then we see that this curve just continues going up. And that's also work with Willi Zwerger and Bernhard Frank, that this curve actually follows for various transport properties, viscosity, thermal transport, almost the extrapolation of the high temperature result. So all the effects of Fermi statistics almost perfectly cancel out. That's quite surprising. And that requires to use, go beyond relaxation time approximation and use a numerically more accurate solution of the Boltzmann equation. Now, eventually, as you approach TC, then this simple picture breaks down and it will still level off and then in the superfluid do other things. So in this case, we see that in a very large temperature window, this kinetic theory works surprisingly well. Right? Usually you would say, okay, here we have a strongly interacting Fermi gas. The Boltzmann approach works by taking essentially ideal fermions and lets them collide. But it's not self-consistent, right? So we find that there are very strong collisions. There's a high scattering rate that would strongly renormalize the properties of the fermions. This is all not included here. So it's, right, it doesn't include the inelastic scattering. It doesn't capture the effect of how particles would move in a strongly interacting medium, right? Because then you cannot really have just a free propagation, then a scattering event isolated, and then free propagation again. That approximation should break down here, but still the simple calculation works surprisingly well. So in a sense, we were lucky. Now, once you have this transport scattering rate, one can go to the use what is called the memory function formalism, introduced in the 70s by Götz and Wölfle, and to say, well, now if you have such a scattering time and you want to get a transport coefficient like a shear viscosity, then this is given essentially by the pressure of the gas times the transport scattering time. So you use this dynamic information, you combine it with a thermodynamic information to get the transport properties. And this time then also allows you to, and basically if you have the finite frequency response, so at zero frequency, it's just this number, but then at finite frequency, a Drude peak results with this typical width that is also given by the scattering rate. Yes, please.
When you say surprisingly well, it's compared to what? Like some in other calculations?
Say experiment and other calculations, the more sophisticated calculations that I will present next.
Okay. And this is like in 3 dimensions?
That is 3D unitary. Right, so in other cases, this will likely not hold. But that is often considered one of the most difficult cases. And so if in that case we find something simpler, this cancellation of 2 competing corrections, that's very useful. We still haven't, I mean, that's perhaps one of the open problems if there is, if it follows exactly this, the extrapolation of the Boltzmann limit. In the numerics, it follows up to 1%. So it could be coincidence. Maybe there is some underlying reason we weren't able to identify one, but that's the status. And so the obvious questions are, well, how can one go beyond, especially if we now want to go near TC where the simple picture actually breaks down. So how can we extend this Boltzmann calculation to when particles also move in medium and are not, say, these asymptotic, non-interacting states that one usually uses? And perhaps a more drastic shortcoming is that here we have the product of F1 and F2, right? So initially you would say you have a pair correlation function that says, okay, if my first particle is in state 1 and the second particle is in state 2, what is the joint distribution for these particles? That is, and then in principle one could use that, and then one would get a whole hierarchy of Boltzmann equations for all these higher particle distributions. Now this is very complicated, and what people then usually do is make this assumption of molecular chaos to say, okay, this is just factorizes into two separate distributions. So each of these particles is independently Fermi distributed. And for many cases at high temperature, that works very well, but it's not always true. And in particular, it's not true when we have bound states, right? As also Yvon described. When we have a bound state, then of course these two particles, say an up and a down, have a much enhanced probability to stay close to each other, and then this factorization is clearly not correct. But it's not trivial to go beyond this assumption of molecular chaos. Now, what can we do if we want to do better? In particular, make no quasi-particle assumption. So then we could use linear response and use a Kubo formula. So you have all seen cases when one computes, for instance, the conductivity of particles, of spin, like say a sigma of omega, then this is related to a current correlation function. So we have, say, current xt commutator with a current operator 0, 0. And then we integrate over space, and we do a Fourier transform in time to this is a retarded response, so we have to integrate only over positive times. Then we have I e to the I omega t minus 1 divided by I omega, essentially. It's doing the Fourier transform minus the static part, and then looking at the linear and frequency part, imaginary part. So this is a well-known prescription how from computing a certain correlation function you obtain the transport coefficient. Now, in linear response means we are looking at small changes away from equilibrium, and that means we can evaluate this correlation function in equilibrium. And here we can now use any method we like, from experiment to Monte Carlo to diagrammatic techniques, what you wish, all with their characteristic difficulties and advantages. So this part is well known. What I like to show you now, where the difference to Boltzmann is perhaps most striking, is for the bulk viscosity. Zeta. And you are sensitive, or bulk viscosity gives you the friction if you do some isotropic expansion. Then this expansion is slowed down due to the bulk viscosity. Now, because it's related to expansion and compression, at high temperature, it also determines the sound attenuation and other things. Now, this bulk viscosity is sensitive to symmetries, in particular the scale symmetry. So as has been discussed by Yvon and Felix Werner, is that if you take such, say, a gas of cold atoms, and you let it expand, then because of the scale invariance at unitarity, the entropy of this state remains exactly the same. Say if it was in one wave function before, it's just in a rescaled wave function, but still a single wave function. And that carries over to thermal states. And that means if no entropy is generated, there can be no dissipation. And in that case, in particular, the zeta is 0. So in the scale invariant case, that vanishes. And if it's not 0, it tells us by how far we break scale invariance. Now, if you want to compute this, this is related to fluctuations of pressure. So we can now similarly write down the Kubo formula for the bulk viscosity with the similar time integral I omega t minus 1 over omega space integral. And now it's fluctuations of pressure between different points in space and time. Now, how do these pressure fluctuations occur? Let's see. So we have generally the pressure as how the energy changes with volume. If we apply this to the zero-range interacting Fermi gas, we can use the formula by Martin and Schwinger that we saw yesterday. And what comes out is that the pressure operator for these cold gases is 2/3 times the Hamiltonian density. This is just a dimensional factor. And if it was scale invariant, then this would be the whole story. But the interaction term is scale invariant only if you go to the unitary case. If you go a little bit away from unitarity, it's no longer scale invariant. And so if you do such a rescaling, you get a correction to this. And this correction is the C operator divided by the scattering length. So you see, if you go to the resonance, this term vanishes, but it quantifies how much you break scale invariance. Now, what is C? C is the so-called contact operator, and it is defined as m squared, bare coupling squared, and then you have the density of up atoms at position x times the density of down atoms at position x. So it's just a double-on operator in the continuum version. Now, if you take these at the same point, then this would be divergent. But if we multiply by the bare coupling, which scales with the range, then this whole product here has a well-defined zero-range limit. So this can be viewed as a regularized form of the interaction operator. Or you could also introduce a gap or pair operator, delta, where this delta of x is just mg0 psi down x psi up x. So basically delta is introduced as the operator that annihilates a local pair. And not by accident, it has this same letter delta as that is usually used for the gap, but it's a local pair. So this contact operator gives you the pairing interaction, but it also counts how many local pairs you have. Now we can interpret this scale invariance breaking term and say, well, how far we go off scale invariance is determined by the strength of pair fluctuations in our fluid. Now, when we have the fluctuations of the pressure and we integrate over space, here on the right-hand side we have the total energy. Well, the total energy is conserved, so that does not give rise to dissipation. But the second term with the contact, this does not commute with the Hamiltonian because it's a local operator. So this contact term is the one that gives rise to dissipation if you go to finite frequency. So we can then say that the bulk viscosity at finite frequency is given essentially by the correlation function of this contact operator of xt 0, 0. And then we have to have the 1 over a squared factor in front, and I omitted other factors. So it's essentially the pair fluctuations. That's basically the delta dagger delta with delta dagger delta correlation that gives rise to bulk viscosity and to shows you by how much scale invariance is broken. So you see, I mean, it's of course it's an old story that if you compute transport, then these operators may have kinetic one-body terms and they may have interaction two-body terms. Here for the bulk viscosity, it is only the two-body term that gives rise to dissipation. So you see that to describe this is harder in the Boltzmann description for single fermions, because even the perturbation, like the way you probe the system, is not accessible to single fermions immediately. And of course, people found ways around this, but this involves a lot more work, also on the Boltzmann level. So in order to compute something like this, it is actually convenient to leave the purely fermionic language, because this is now a 4-point vertex, right? 2 fermion lines going in, 2 out, and so this is a high, like an 8-point correlation function. That's not nice. So what we do instead, and that is also joint work with Willi Zwerger, is to use a self-consistent conserving approximation that we call the Luttinger-Ward approach. And the idea is to work here with, or introduce a new field for the collective pair excitation, so Hubbard-Stratonovich transformation if you wish. And then the zeta can be calculated, well, if we now express this correlation or response function diagrammatically, say here we have such a contact vertex and here another one, and so you have a pair going one way and a pair going the other way. So this is a kind of pair hole bubble. And it tells you how, well, taking this seriously, so the C operator absorbs a pair and generates a pair. And then there are vertex corrections, right? So this will be a renormalized vertex here. Now, these vertex corrections involve an interaction between pairs, right? That will be the first correction. And so we will have the contribution where the pairs are actually not interacting, but then the leading correction where we include the interaction between pairs comes from the following process. It is you start out with a pair, but then this pair splits up. And one fermion is circling right back, and only the other one continues. So you have now that the pair is excited, it splits up, it dissociates, and comes back. So we have now two perspectives on this. One is to say, okay, this box here has 4 pair lines going in, so it's essentially an interaction between pairs. That's what we were expecting from vertex corrections. But there is an alternative perspective, and we can say, well, here in the middle, it looks just like a fermionic contribution. So we can also say here on the left, this is the pressure variation excites a pair, but then after this dissociation, it gives rise to an induced viscosity vertex for the fermions, right? So the whole orange box has just two Fermi lines coming out, and then the same thing on the right. And this is something that one can actually do, and one can say, okay, now we take this as our starting point for a fermionic transport theory. And this, there is a Boltzmann calculation by Dassling and Schäfer for the bulk viscosity, and it actually corresponds to doing precisely that. They argued it in a different way, but it says how do these pair fluctuations induce a pressure on the fermions, and then you do the standard transport calculation for the fermions. This gives some part of the result, but we see that if we include this contribution, which is just outside the fermionic Boltzmann, we get a result that is about 5 times higher. So it does make a big difference. And then there are further corrections. So this approach is now, or we can basically include higher orders. There will be infinite ladders to be resummed. And this is something we do numerically. We have these green functions and the renormalized vertices stored as functions of frequency and momentum on some grid. And we solve these self-consistent equations numerically to obtain then finally the bulk viscosity as a function of frequency. So here, let me draw a squared zeta at unitarity. And at small frequency, it has some value. Then as you increase the frequency, it looks like a Drude peak. But then at higher frequency, it changes behavior and goes down a bit more slowly. So here you have scaling that can be written as chi tau over 1 plus omega squared tau squared. This is what we call the Drude regime up here. And down there, it is essentially the contact expectation value divided by omega to the 3/2. So it's some non-analytic behavior that at high frequencies comes from the peculiar properties of this short-range interaction. Yes?
Do you collect modes at what temperature would be here now?
So qualitatively, you see this in the whole normal state above TC.
Okay, so you're going to stop at low temperatures also?
Yeah, so basically we solve these equations at all temperatures above TC, down to TC. It's not yet with Nambu propagators for the broken state, but and qualitatively these pieces are always seen with, but their relative weight changes. And so this chi is then the sum rule that we get by integrating this bulk viscosity over all frequencies, so it's a finite number. And now we know the contact. It's one of the thermodynamic properties of our system, basically the typical pair density of fluctuating pairs above TC where they're not condensed. But then the question is, what is this transport scattering time? Or let's plot this kind of transport scattering rate so you don't have to invert too many times in your head. And here we find something very remarkable, that it just keeps going linearly up. So somewhere here is the Fermi temperature, and where all the other transport properties will then have a reduced scattering time, this one keeps going up. This is a very surprising feature. So this is a very nice quantum critical scaling that goes up beyond the quantum degenerate regime. It's just proportional to t, right? So it means that the scattering rate is kBt over h bar with a number here in front that is of order 1. 1.6, I think. So the fact that this scales so differently from the other properties like shear viscosity, thermal transport, and so on, is related to this pair aspect of the transport. Right? It's basically the transport scattering rate goes like the thermodynamic susceptibility that involves how the thermal probability of exciting pairs, which is quite low because you need to excite two particles at the same time. It goes like fugacity squared, but then divided by the transport time, which also has basically this here goes like fugacity, and this one also goes like fugacity. So you see that all factors of fugacity or density cancel out in the numerator and in the denominator, and we have something that is density independent up to high density. That's quite interesting. And sorry? Well, it goes up. Well, in the calculation, it would go up to the microscopic scales, like van der Waals scale, right? I mean, this is what comes out of the virial expansion at high temperature. So when you can apply virial expansion, you get this. And so this calculation is numerical. It's a bit involved. So an interesting open question is, can we find a simpler effective model that captures this interplay between fermions and pairs? Right, to have basically a Boltzmann equation for fermions and pairs that captures much of that. Perhaps inspired by the success of Boltzmann for the fermions alone. And something we did last year with Keisuke Fuji, who is a postdoc in our group, was to solve this in the high temperature limit. In the virial expansion, this can be solved. And in high temperature, all the scattering is on shell. So then one can basically reformulate this set of equations as a Boltzmann, linearized Boltzmann equation. And then one can just read off. So then one gets essentially a coupled Boltzmann equation for the fermionic distribution and for the pair distribution, which are both a bit off equilibrium. And that works nicely and recovers the known results, but then we would like to, or what is the open question is how this could be extended to the degenerate gas where we don't have the precise prefactors anymore from the virial expansion.
Down to which temperature does that approximation then give the result which you got sort of from the Latinger board?
Okay, we haven't checked yet, actually. No, I mean, at high temperature, the Latinger Ward and Boltzmann give the same. And we find it from the Latinger Ward that it is almost a straight line. So there are like 10% corrections to that, essentially down to 2 times Tc or so. So, okay, I used up all my space. Let's start with the first one again. So now a question is, how can you measure this bulk viscosity? And there's a very nice proposal by Fuji and Nishida from 2018 that use a very simple argument and say, well, so the way we introduced it was to say we look at some isotropic expansion. And then if there's friction, that determines our bulk viscosity. But by universality, near the scattering resonance, everything depends just on the ratio of scattering length to particle spacing. So that now allows one to do it actually the other way around and to say, well, I keep my gas fixed, but I change the scattering length. In this way, I have similarly a way to tune the ratio between the two. And changing the scattering length, fortunately, is very easy with cold atoms if you're near Feshbach resonance. So basically the idea is, okay, either you have a fixed scattering length A and you let the cloud expand, or equivalently you can take a fixed cloud and make the scattering length, now how should I draw it? Make it smaller, right? That gives you have basically a time-dependent scattering length that accesses the same transport properties, because if you take the fixed cloud and you change the scattering length, the system will locally go out of equilibrium and it has to relax back by bulk dissipation. So what happens then is that you ask the question, how does the contact behave sometime after you change the scattering length? Right? This is now time dependent and you're doing linear response and asking how does the contact change sometime after. Now that by linear response is related to this contact correlator, which again, as we saw, is related to the zeta. So in this accesses the bulk viscosity. Now, the proposal is simple, to say, okay, here we do now a time-dependent thing. We say we have here the scattering length, A inverse of time, and here is 0. Here's 0 inverse scattering length is unitarity. And now we go a little bit around that point. So we say this is like a sine omega t. So the scattering length is now oscillating around unitarity. Now what does the contact do? If you do this very slowly, then the contact would just follow. Let's call this the equilibrium contact evaluated at the instantaneous scattering length. This is kind of the quasi-static. But if you do it more quickly, because it's a dissipative process, the contact is not able to follow immediately. And so it will take some time to grow up and then do this. So this is the actual contact as a function of t. And so you see there is now a phase lag, phi, that tells you how strong the dissipation is. And we have computed that if you now plot this phase lag, it eventually has a peak when the frequency matches the scattering rate of bulk viscosity. It has a maximum there. Now, this experimentally is quite nice because it needs, well, it needs a time-resolved measurement of the contact, with several groups can do below 1 millisecond. So this is, and we are presently working with the group of Joseph Tywison to, I mean, they are doing this experiment and we are analyzing it together to extract the bulk viscosity and the bulk scattering rate directly. It's very nice because a phase shift doesn't require calibration of the absolute value, so it's a quite robust measurement. And it gives you access now essentially to the whole zeta of omega. So there are not so many examples where you can actually have the full dynamical transport coefficient, not just in the small frequency hydrodynamic limit. And now there is, if we put the pieces together, we just discuss that, or we have the theory prediction that this scattering rate is quantum critical. It's proportional to temperature, but more or less independent of density. Now that means that if you have, for instance, a trapped gas, then the parts in the center at high density and the parts at the edges at low density all relax at the same time scale. So you can just do a transport measurement in the trapped gas without hurting your analysis. Right? So that is quantum critical scaling helps you a lot in kind of rehabilitating the trapped gases, because you can, because the quantity you're looking for doesn't even depend on density. And that could, of course, then now if you would record this curve for different temperatures, say at one temperature you might get this curve, at a higher temperature this, and a yet higher temperature this. And then, of course, the way to test this theoretical prediction of quantum critical scaling would be to plot omega over t, and then all these curves would be expected to lie on top of each other. This is what we now want to study. Now, this frequency dependence of transport gives us access, as I said, beyond hydrodynamics, also to faster processes. And the question is, is there something interesting to learn if we look at faster changes? And a topic that has been discussed in heavy ion collisions is, in the last, 10 years or so, is this, say you have two heavy ions, they are colliding, they are Lorentz contracted, so they look like pancakes, and then after the collision it's some very highly excited state. Surprisingly, one finds that already after very short times after the collision, this can be described as a fluid evolution, long before hydrodynamics is expected to be valid. And this so-called fast hydrodynamization is a surprise, a puzzle, and there have been various theoretical models that try to model and explain this, some put forward by Michael Heller 10 years ago, for instance, and that goes roughly by the idea, so you say here you have some deviation from equilibrium. For these heavy ion collisions, it's the difference between longitudinal and transverse pressure, whatever the details. And here you have time. And the statement is that you start from different initial conditions, you get some family of curves, and the remarkable thing is that after something rather short, say on the order of a transport time, all the curves for different initial conditions converge to a common curve that for long times will then merge into the usual hydrodynamic result. And that is called the hydrodynamic attractor. This comes from model calculations, from kinetic theory, holographic duality, and so on. In experiment, it's not so easy to see, because in the heavy ion collisions, you mostly see what comes out in the end, but not the movie. But to see if this goes to hydrodynamics, you actually need the movie. So the idea was that perhaps we can observe something of this kind with cold atoms. And so then the physics questions involved here are, well, if hydrodynamics is valid here at long times, what comes before? Of course, these individual curves depend on initial conditions, but are there maybe some generic equations how it should go before hydrodynamics comes fully valid? Put a different way, hydrodynamics is a gradient expansion in, say, omega t, omega tau. Right? If this is small, then you have the usual Navier-Stokes equation. If this is large, and then you can go to, say, second order hydrodynamics, include relaxation times, and so on. So the question is that if we want to describe earlier times, can we go to higher orders of hydrodynamics to see what happens here? That's kind of the framework. And now we made an explicit calculation for this for cold atoms. Again, this is work with Keisuke Fuji, who is now just became assistant professor in Tokyo. And the idea is that we change the scattering length. Now, so basically take this idea, but do it a bit differently, and consider something where we have a scattering length that will eventually approach unitarity, but you start a little bit off. So this, say, is you drive externally your scattering length to start a bit away from unitarity, and then for a longer time you approach unitarity. So first, say for negative times, it's here in an equilibrium state at some initial scattering length, and then at some initial time, you start changing. And first you change fast, and later you change slowly. And one can take, say, a certain, say, a power law of time. This is just some model protocol that we use for the calculations and to discuss the character of the results. Now, what we want to do is to actually try different initial conditions. So what we can then do is to say, okay, either you start here and then follow this trajectory, or you start here and then from this time on follow this trajectory, or you start even closer to unitarity, but then you follow the same curve from a later time on. So you have different initial conditions. And the question is, what happens now to the contact, right? We still have the same observable. And so if we do linear response, let's go, which tableau is this one? So from linear response, you find that the change here should be essentially given by this correlation function, t prime integrated over t prime times the change of your scattering length, right? This is linear response. So given this particular way of changing the scattering length, we can compute what the contact should be doing afterwards. Now, for this correlation function, we can use our hard-won input from this microscopic numerical calculation for the bulk viscosity. We had it in frequency. We can do a Fourier transform and see how this looks like in real time. Still, if we look at fast changes, but with small amplitude, we should still be in the linear response regime. So we can use these existing results. And now the outcome was that in the relevant time scale, say roughly on the order of the transport time tau, it's essentially the Drude peak that governs the response. So we can express this as chi over tau exponential minus t over tau, roughly, or the time difference one should put in here. And then at very short times, there will be these contact things, but the short times are non-universal anyways. At very long time, instead, one may have the effect of hydrodynamic fluctuations that give a power law instead of exponential, but that is, say, beyond where we are looking. So the Drude should be actually a very good representation of our numerical data for the bulk viscosity in the relevant region. So now this is almost an exercise for students to say, okay, now do this integral. So we have an exponential decay times a power law. Now, these integrals are well known. It gives some incomplete gamma functions. We'll come to that in a second. So this can actually be calculated. And what one finds then is, say here in this case, the actual response of the contact is always a bit slower, right? Because it has this time scale. So it will here go there and then eventually go down. If you start with the blue one, it will go here and then go down. The white one will go here and then go down. So again, we see that there's some, of course, the initial conditions differ, but here there is still this common region where they converge to what can potentially be an attractor. And that is basically an experimental signature if one can measure the contact quickly enough. So, I'm on time.
It starts to become universal, it's just a few times tau.
Yes, exactly.
A few means 3 or whatever.
Yes. And 5, perhaps. And so we can calculate this in our model. Now we wanted to compare to hydrodynamics because that was the outset, right? Does it give a behavior that is different from ordinary Navier-Stokes, right? One could also do Navier-Stokes for this kind of protocol and just see what one gets out. So for the comparison with hydrodynamics, it is actually interesting to see how one would capture such a change of scattering length within the framework of hydrodynamics. So the question is the following. So you have a change of scattering length that comes from a change of magnetic field near the Feshbach resonance. Now, in a fully microscopic model, you would have your van der Waals potential, the bound states, and so on, and you will get this. Now, this, on the kind of coarse-grained model, say on the particle spacing of our atoms, all these details about the electromagnetic fields are no longer visible. What you have is just this changing scattering length. And this now enters our effective model essentially as a generalized external field, if you wish. Right? So you could, basically your Hamiltonian has, let's write it differently. Say, let's write the continuity equation for the Hamiltonian. Then we have some energy currents. And we have the, say, external force times velocity, or operators. And now we have essentially the contact operator times the change of 1 over t, right? So you get an additional term in your energy continuity equation here on the operator level that is generated by this kind of generalized external field. And if we have an additional external field in our low energy effective Hamiltonian, it's no surprise that it propagates through all the derivation of hydrodynamics. So what you then do is you say, well, what you have is that the stress tensor operator, the trace of it, is 2 times the Hamiltonian plus c over 4 pi m a of t. You combine that, that's the pressure relation we had much earlier. You combine that with the constitutive relations for the gas, and then you do the usual steps of hydrodynamics. And what comes out at the end of the day, that's this work by Fuji and Nishida, is that you say you define a small pi of x that is basically 1 over dimension the trace of, the dissipative part of your stress tensor. Not the pressure one, but the one that is due to dissipation in the usual hydrodynamic sense. And this arises from, so basically the dissipative part of the stress tensor comes from the bulk viscosity times a driving term. Here this driving term, VA, would be usually for bulk viscosity comes from isotropic flow, right? That was also the picture that we had initially. So divergence of velocity. But when you allow to change this scattering length, you get extra terms that have a dt plus v dot gradient log a. Right? So if the scattering length is time and space dependent, you get an additional term that also generates bulk dissipation. And this is basically the hydrodynamic manifestation of saying, okay, it's equivalent if you either isotropically expand your fluid, then you have a certain radial velocity profile that gives rise to the first term, or you say you have a change in time of your scattering length that is equivalent on the level of hydrodynamics. And this quantity, if you again use these relations, can also be expressed as the instantaneous contact minus the equilibrium, 1 divided by A of t essentially. And this quantity here is also called the bulk pressure. It's basically the dissipative contribution to the pressure in hydrodynamics that arises from the out of equilibrium contact. So now this is should be this one here. Now, so the upshot of this hydrodynamic treatment is that we can express, like if we are in 3 dimensions, we put d equals 3 times zeta times VA, and for this we now say our the scattering length depends only on time but nothing else, then this gives rise, this change of scattering length times the bulk viscosity gives rise to how far we are out of equilibrium. So this is the usual hydro, and that is on the Navier-Stokes level. So then we have something to compare, right? That's the hydrodynamic prediction. Now, our actual case where we have this exponential decay on the time scale of the scattering time tau can now also easily be incorporated by an extension of this equation by saying, okay, now we add a decay term. Say this is the pi of t, and then this additional term tells us that now if we do some drive here on the right-hand side, this thing responds, but not instantaneously, but with a certain time lag. Yes?
So your A appearing in the log can be positive and negative? Is dimension full or dimensionless?
It's
dimensionless, presumably, and also positive, yeah?
It doesn't need to be. Think of A dot over A. I think the sign doesn't really matter.
No, but the log appears here also before that.
You take derivatives of the log. So it's always the derivative of A divided by A, and so the units cancel out. Yeah. Yeah, it can be positive, negative side. That's not an issue here. And so when we now take this kind of dynamical equation with this particular drive, then we can solve it quite easily. What we get then is that this pi of t has some part with the initial conditions. Let's call it pi ini exponential minus t over tau. And an additional piece that I call pi attractor of t, where you see that these initial conditions, they will decay on the timescale tau. And that is also, no, I'm afraid I erased it. Okay, so the particular starting point decays quickly on the timescale tau. And then there is another piece. And this other piece, now for the power law drive, can also be given explicitly by this scale susceptibility chi. Then it has also an e to the minus t over tau, and now comes the incomplete gamma function that I told you about of argument minus 2 alpha and minus t over tau. So we have a full analytical solution here, and being able to express it in this way helps us in our analysis, because for this function we know the asymptotics, which is not so trivial. And you see that this attractor solution depends on alpha. That is the exponents, how quickly we do the drive. That is just our protocol that we impose. And then it depends on the chi and the tau. These are the intrinsic properties of our fluid. But it does not depend on the initial condition. It doesn't depend at which time and at which initial scattering length we started this. Right? So it just depends on the trajectory that we do in our probe. So this is why we call it an attractor, because for all these curves, they only differ by the quickly decaying initial part, but then the remainder is the same. And now this function can be expanded. So if we want to make contact with hydro, we expand for long time, where, say, tau over t is a small number. And in that case, this attractor solution will be roughly like, now let me get the powers right. So it's tau over t to the power 1 plus 2 alpha, and then you have 1 plus 2 alpha plus 1 tau over t plus higher powers. Okay, the first contribution here, the 1, is the Navier-Stokes that we had before. And this next term, so that's the leading term at long time. Then you have some corrections at long time, subleading, that, well, are beyond Navier-Stokes. These are sometimes called second-order hydro, and then one just continues these powers. While the initial condition here, if you expand for long times, it's e to the minus 1 over your parameter here, so it's non-perturbative. So at long times, this decay of the initial state is a non-perturbative contribution that is just outside hydrodynamics. You can't see it at any order in this expansion. And this is therefore also called a non-hydrodynamic mode in the jargon. Okay, so great. We have a series expansion that gives us the corrections to the long-time behavior. But if you look carefully at this, you see that these higher powers come with factorially growing coefficients. So these coefficients for the nth term scales like n plus 2 alpha factorial. Now that's bad, because it tells us that this power series converges very badly. Now, of course, there are experts in the room on Borel resummation, and this is in fact what one can do. So one can take all these higher orders, Borel resum, now with the slight modification that you don't do it with the n factorial, but n plus 2 alpha factorial, and then one gets back this exact solution with the incomplete gamma function. So one could approach it, and that basically the Borel resummation was also how we did it first. We computed order by order, and we were very happy that we could Borel resum and get a nice analytic result. That is fine, but in the end, solving this differential equation turned out to be much simpler and give, of course, the same result. Now, for short times, instead, this gamma function is also non-analytic. It involves logarithmic terms and so on. So it doesn't have a good series expansion either for long or short times, but then, of course, this solution includes everything. So now let's put these things together and plot this deviation from equilibrium versus the thermodynamic susceptibility to get something dimensionless. And here we have time. So here we have tau, and now in this scaling, let's see, we get a, let me first draw this. So this is supposed to be the attractor solution for different initial conditions. We get a whole family of curves that converge to this attractor here. And now we can answer the question how this compares with standard hydro, with Navier-Stokes. So you take just this one, or here the leading order, and then you see that Navier-Stokes would be here. Now you can include the second term, go to second order hydro, and you see it's already a bit better. But then this whole attractor solution is kind of the asymptotic result of going to infinite order. And now you see that there is, if the different initial conditions are around the scattering time, then there is now a window for seeing this attractor, say, well, if we put in specific numbers, say between 6 and 12 times tau, and after that, it's indistinguishable from Navier-Stokes. So one really sees that there is fluid flow that is specific for short times, different from Navier-Stokes at early times. And in experiment, you could measure the contact step for different time slices and actually have a movie of flow beyond hydro. Now, open questions in this regard are clearly the precise curves one sees here are dependent on your protocol, right? The attractor solution depends on the alpha, so how we do the ramp toward unitarity. So that is clearly not universal, but perhaps the equations could be. So here we use something like second order hydro that is an extension of simple one with an extra one more term on the level of the differential equation. Now, of course, the solution has many higher orders, but the differential equation only has one higher order. Right? But if you go higher, then of course you have a lot of freedom what you add, right? Which all at long times shouldn't matter. And the question is if one can find something more general for shorter times after changing the system. Now, on the technical level, these transport calculations that I've shown you were done in imaginary frequency, summing up all these diagrams. We have quite recently implemented also a solver for these equations in real frequency in the Keltisch formalism, still at equilibrium. Non-equilibrium is then the next step. And I think that is one of the big open problems, to study this really out of equilibrium, not just in linear response. And that is becoming a very numerical task. But so in principle, it's clear what one should do. But then there are many steps to actually get the fully renormalized fermions and pairs over the time evolution. And especially if one works in real frequency, there's, earlier Antoine Georges mentioned the compression of basically the degrees of freedom that we need to efficiently describe such a situation. Also for the spectra, well, we don't expect an exponential improvement, but at least by a large factor, by finding good spectral representations, right? If you have a simple pole, that's of course easy. For these problems, typically you have branch cuts, but could there be a good way to tell us how our green functions, what is their analytical structure, where do they have poles and branches, in order to have basically focus on the important excitations or continua that there are, to have a more physical parametrization of these quite complicated green functions. Yes, and with this I would close, and looking forward to your questions.